This is chapter 12, the regression line, part 2. First, we're going to talk about some cautions. The first one is that association is not causation. So a regression line describes the data that you see, but it can't be relied on for telling us how Y will respond if our investigator changes an X value, unless it's a controlled experiment, because in an observational study there are just too many confounding factors. So for example 99, for California women, the slope of the line for predicting income from education is 2,176. So what does this tell us first? What can we get out of that one statement? First, we can figure out what X and Y are. So we want to predict income from education. So Y is income and X is slope. Sorry, X is education. Our slope always tells you rise over run, and in our case our slope is 2,176, and then we can put over the number 1 to make it a fraction. And so what does this say? It's basically saying, so if education goes up by 1 year, the average income goes up by 2,176. So the first true or false statement says, associated with each year of income, there's an increase of 2,176 more in income on average. Okay, that is true. Okay, again, that associated with, that's kind of our key word. We're not doing a cause and effect. We're just saying that on average, when you get another year of income, or another year of education, the average income goes up by about 2,176. Okay. The next statement, though, going to school for an extra year will cause an increase of 2,176 in income. That one is false, because we can't say there's a cause and effect. This was just an observational study. They didn't take California women and force them to get different amounts of education to see if increasing their education changed their income. They just looked at people that were already educated and asked them what their income was. Okay, and so you can't say that if you just go to school for 1 more year, you will get an additional $2,176 in income. Our next statement, those who have a 4-year degree will earn on average blank more than those who only completed high school. So let's try and figure out first what that blank would be. So if you have a 4-year degree compared to high school, that means X goes up by 4. So if X goes up by 4, Y should go up by 4 times the slope. Our slope is 2,176, so this is 8,704. So 8,704. So let's read it again. Those who have a 4-year degree earn on average 8,704 more than those who only completed high school. And this is okay because we just said on average. We're not talking about a cause and effect. We're not talking about individual people. But on average, this should be correct. So this would be true. The next statement, getting an extra 8 years of schooling will cause someone's salary to increase by blank. So let's do the same thing. So X goes up by 8. Y should go up by 8 times the slope, which is 2,176. So this is 17,408. So getting an extra 8 years of schooling will cause someone's salary to increase by 17,408. So we filled in the blank. Now if we evaluate this statement, notice it's saying getting an extra 8 years of schooling will cause someone's salary to increase by this amount. So there's 2 things wrong here. We said it's cause, and we can't say cause and effect because it's just an observational study. Okay, also we just said someone, and individual people were never exactly on the line, so this probably isn't going to be correct. It's a lot safer to say on average than to try and predict it for one person, because your predictions for one person are going to be further off than the predictions for an average. The next point we want to make is that your intercept might not be logical. We already saw this in our last video. So for example, if you were predicting sales price based on the weight of a product and you discover that the price for a £0 product is negative $23. And this doesn't make sense because no one's going to pay you $23 to take the £0 product. Now this doesn't mean that your y-intercept is wrong, it just means that we picked the y-intercept that makes our line the best fit for the data. It is possible to force a line to go through the point 0, 0. So like in this example, the point is going through 0, 0. And it might have a practical interpretation. So something like if you have a £0 product, it might cost $0. But notice, so this example, we have the same data set. And here I let the intercept vary to where it fit the data the best. And notice it fits the data pretty well. But over here, I forced the data to go, the line to go through the intercept y equals 0, 0, or the point 0, 0. And notice that now the line doesn't fit the data. So again, we don't really care about the interpretation of the intercept as much as we care about just making the line fit our data well. Next we have extrapolation. So you shouldn't use regression to predict values that are outside the range of your data. So extrapolation is when you use a regression line for predictions, but the x values are far outside the range of the x values used to obtain the line. And we do sometimes extrapolate if it's the only information we have, but the predictions we get from that are usually inaccurate. Because we can't guarantee that the relationship between our x and y values remain the same for different x values. So let's look at these examples and see what I mean. So on each one, it's the same data set to start with for our data values. So we had a specific range of x values that our data was in. So here's our specific range of x values. And for my first example, if I was to draw in a line, or draw in the line based on the data inside our data values, it does, on this example, appear to fit values way up here, and so this prediction might be accurate. But if I look at this example, so that was only one possibility. Over here, if I fit the data, the line, again, based on the data that I actually have, and now let's say I want to predict for this x value, is that x value going to be, or is that prediction accurate? No. Or over here, if I fit the line, notice that the trend changed. It was the line, and then all of a sudden, my points ended up just kind of leveling. They jumped up and leveled out. So if I was to make a prediction here, it's not going to be accurate. If I make a prediction here, well, that one happens to be accurate, but most of the rest aren't. Or again, for this one, notice that suddenly my data curved up. And if I make a prediction out here, it's not going to be accurate. So the point to learn here is that if you try and predict for x values that are way outside of your original data, you don't know if it'll be accurate because you don't know if the data continues the same relationship that you saw. Or if it suddenly curves up or down or jumps up, you just don't know. Two more cautions. First, a regression line can be found for any two continuous variables. So if you put the data into the computer can give you a regression line. But that doesn't mean that it's going to be accurate or make sense. You need to think about it yourself. So if there's a nonlinear relationship between the variables, that means it's not a line. That means it could be like a curve. So if we have curved data, and then I try and fit a line to it, it's not going to fit the data very well. There's also sometimes that your regression could end up being something silly that doesn't really make sense. Like trying to predict the area of a square based on the color of the square. Well, the color's not continuous, but the area of the square based on the number of sides of a square, something like that. That might not make sense. So let's talk about what's called least squares regression. So for any data set, many lines could be drawn through our data. The best line would be the line that's the closest to as many data points as possible. So we're going to go and use an applet to demonstrate this. What we want to do is we want to find the best line by finding the line with the smallest RMS error. And it turns out that this is actually going to be the regression line we've already been using. But let's go try. In this applet, we can check the correlation, and we can try to fit our line. So what we want to do is we are trying to move this line around, and as we move this line around, we're trying to find the line that's the best fit for this data. And the way that we can find the line that's the best fit is we want to find the line that has the smallest RMS error. Now down here you'll see some numbers. You'll see the equation of the line, and SSE and MSE. So this is written for another class, so they don't use the words RMS error. But RMS error is about the same thing as MSE. So what we're going to do is we're going to drag this line and we're going to look for the smallest possible MSE we can get. So I'm dragging it around. Notice my MSE is like 10.12. Now my MSE is 12.1, 14.67, 10.03. So I haven't really gotten it any lower than 10. Oh wait, there's a 9. So you can see that we can drag along and we're trying to find the line that has the smallest MSE or the smallest RMS error. So that's my line. That's what I think is the best. Now I'll ask the computer to do it. And they found the smallest MSE was actually 9.66. So they found an MSE with a line with a smaller MSE than we did. So this green line, the least squares line, that's going to be the best possible line to fit the data. The data that comes the closest to as many points is just the best fit. And it turns out that the regression line that we've already been using is this line of the best fit. And we call it the least squares regression line sometimes because we squared the errors when we were finding the RMS, and then we found the least of the RMS error, and so it's least squares regression line. Example 100 is about California men and their years of education, as well as their income. So number one, we want to find and interpret the slope of the line for estimating income from education. So notice because we're estimating income, that's what we're trying to predict, so y would be income, which means that x must be the number of years of education. So if I want to find the slope, we're going to use our formula. Slope equals r times the standard deviation of y over the standard deviation of x. R is 0.25 times the standard deviation of y. Make sure you're using the standard deviation for income of 24,000 divided by the standard deviation of x, which is 3. This is going to give me 2,000. This means that on average, as education goes up 1 year, then the average income goes up $2,000. Now just keep in mind that this is talking about association, not causation. So on average, if you get an extra year of education, then your average income goes up by $2,000. This doesn't mean that you specifically will have an extra $2,000 of income if you go to school another year. But on average, this is what we predict. Next, find and interpret the intercept of the line for estimating income from education. The intercept equals the average of y minus the slope times the average of x. The average of y is 30,000 minus our slope of 2,000 times the average of x, which is 12.5. This gives us 5,000. Now what does this mean? What is our interpretation? For the intercept says, well, if x is 0, what is y? So if someone, or on average, if someone has 0 years of education, their income is $5,000. Now we want to find the equation of the line for estimating income from education. We know that any equation of the line is y equals our slope times x plus the intercept. So in our case, y is going to equal 2,000 x plus 5,000. Now you can leave that as your final answer. I like to go ahead and put in words instead of x's and y since this is a statistics class. So I might say something like income equals 2,000 times education plus 5,000. And this just helps me remember which variable is which. So number 4, estimate the income of a California man with 4 years of education. So this means that education equals 4, and all I have to do is plug that education equals 4 into the equation of my line. So the income was equal to 2,000 times the years of education plus 5,000. So all I have to do is put in 4 where I see education. So 2,000 times 4 plus 5,000. This gives me 13,000. So, on average, people in California with 4 years of education make about $13,000. Number 5, predict the income of a man with 16 years of education. So now, education equals 16, and we're going to do the exact same thing. Now we just plug in 16 for our education. So it would be 2,000 times 16 plus 5,000, which gives me $37,000. So for this man that has 16 years of education, we predict that his income will be about $37,000. Now number 6, I've actually shown you the graph. This is what our actual data looks like. Notice there's an interesting problem here. The points are closer to the line down here for the lower level of education, but the points are really far apart, are really far away from the line for your higher level of education. So what this means is there's a lot of variability when your level of education gets higher. There's less variability when you have less education. So even for this man with 16 years of education, we predicted that he was going to get $37,000. That's this point right here. But notice there's some men with 16 years that are making a lot of money, and some men that are making not very much money. So there's a lot of variability here. Okay, so let's find our RMS error. Remember, that's the square root of 1 minus r squared times the standard deviation of y. So it's going to be the square root of 1 minus 0.25 squared times the standard deviation of our income, which is 24,000. So this equals 23,237.9. That's a pretty big RMS error. What does the RMS error tell us? The RMS error tells us that 68% of our predictions should be within $23,237.90 of the true values. And 95% of our predictions should be within 2 times $23,237.90 of the true values. So that means we're really not that close. Our results really aren't that accurate. But you notice how this problem has all these stars? I put those stars there for a reason. And do you remember how I said that the variability was changing based on the education level? That you had a small variability here, and a bigger variability, and then a really big variability, or your vertical spread is changing. So you probably don't remember this, but in chapter 11, we said you can only use the RMS error. The RMS error only makes sense if you have a constant vertical spread. So in this case, our vertical spread is not constant. So you shouldn't use the RMS error. Really, you shouldn't use regression either. So this is a good example of you should always check your data before you get too excited about making your predictions, because the predictions we're making might not be all that accurate. For number 7, so let's continue along this line of thought. Do you think that our estimate is likely to be more precise for the man with 4 years or the man with 16 years? So if we were at 4 years, that would put us about here. Four years puts us about here, so we have about this big of a vertical spread. 16 years puts you here with this big of a vertical spread. So which estimate do you think is more likely to be precise or more precise? I would think that the man for 4 years, that estimate should be a lot more precise because there's not much variability, there's not much spread in our actual data. Whereas for 16 years, there's a very big spread of what people are making when they have 16 years of education. So I would say that probably the man was 16 years because there is less vertical spread. So sorry, that's not what I meant to say. I meant to say the man with 4 years because at 4 years there's less vertical spread, so less variability. So we are more likely to be close to the true value. Number 8, estimate the income for a perpetual student who has 40 years of education. Now, what do you notice about 40 years of education? If I was to come back up and look at my data, 40 years of education, that's going to be about here. Does my data go all the way to 40 years? No, it's not even close. My data only goes to about 20 years. So this is what we would call extrapolation. So yes, I can predict it. I can say, so income equals 2,000 times 40 plus our intercept of 5,000. And this gives me 85,000. But this was extrapolation. "40 years was very far from our original data that only went from 0 to 20 years. And so because it was extrapolation, it probably isn't an accurate prediction. For our last problem, Suppose for newborns the average weight is about 7.5 pounds with a standard deviation of 0.8, and their average length is 20 inches with a standard deviation of 1.25 inches, and the correlation is 0.6. Number 1, find and interpret the slope for predicting newborn weight from length. So if I was to summarize this, x has to be our length because we are trying to predict the weight. And the average weight, so they actually told me weight stuff first. So weight, the average is 7.5 and the standard deviation is 0.8. For length, my average is 20, the standard deviation is 1.25, and our correlation is 0.6. That will help me to have everything summarized. Number 1, find and interpret our slope for predicting newborn weight from length. Again, slope is r times the standard deviation of y over the standard deviation of x. So our correlation r is 0.6, the standard deviation of y is 0.8, the standard deviation of x is 1.25. So this gives me 0.384. How do I interpret this? We say if x goes up by 1, so if length goes up by 1 inch, so if length goes up by 1 inch, we predict the average weight will go up by about 0.384 pounds. So for each additional inch, the average weight should go up by about 0.384 pounds. Number 2, find and interpret the intercept. So for our intercept, that's going to be our average of y minus our slope times the average of x. The average of y is 7.5, our slope is 0.384, and the average of x is 20. This gives me negative 0.18. Now, what is the intercept? Remember, our intercept is if x is 0, what is y? So if length is 0 inches, we predict the weight will be negative 0.18 pounds. You notice this is not a logical intercept, which is okay. That doesn't mean it's wrong. It means it's just the best fit, or the intercept that makes our line fit the data the best, but it's not very logical. First of all, you're never going to have a baby that has a length of 0 inches. And secondly, their weight's not going to be negative. So obviously this one is not logical. Number 3, find the equation of our regression line for predicting weight from length. So y equals our slope times x plus the intercept. So in our case, y equals our slope of 0.384 times x plus, or in this case, minus our intercept of 0.18. And we can write it in context. So weight equals 0.384 times the length minus 0.18. Number 4, use the regression line to predict the weight of a baby who is 23 inches long. So length is 23. And all we have to do is plug it into our equation. So our weight equals 0.384 times length minus 0.18. So if we just plug in our 23 inches for length, 0.384 times 23 minus 0.18. This gives me 8.652 pounds. Number 5. About how much error do you expect in your prediction? Anytime we're asking about this, this is going back to the RMS error, which is the square root of 1 minus r squared times the standard deviation of y. So the square root of 1 minus, our correlation is 0.6, so 1 minus 0.6 squared times the standard deviation of y, which is 0.8, and this gives me 0.64. So we expect about 0.64 pounds of error in our prediction. Okay, or in other words, for a 23-inch baby, we expect it to weigh 8.652 pounds, give or take 0.64 pounds. So we expect to be off by about 0.6 pounds. Number 6. Statistically speaking, would you be surprised to find that a 23-inch baby weighed 6.5 pounds? And explain. So we expect to be off by about 1 RMS error, and we really expect to not be off by more than 2 RMS errors, because we expect 95% of babies that are 23 inches long to be about 8.652 plus or minus 0.6 or 2 times 0.64 pounds. So be within 2 RMS errors. So they should be within, if I minus it, I get 7.372 pounds. And if I add it, I get 9.932 pounds. So 95% of the babies that are 23 inches long are going to be within 7.3 pounds and 9.9 pounds. So 6.5 is outside of that range. So it would be surprising.